Tens of billions of dollars are generated every year by the electrical wire industry in the United States alone. Why does such a seemingly simple component command such immense economic value? It only looks obvious that wire is merely a conductor, but in reality, these coils manage the total flow of energy required to sustain modern civilization. Behind every single foot of this material lies a foundation of strict engineering and physical constants. One can notice how highly refined copper is drawn through a series of precision steel dies to achieve exact dimensions. This process is only gaining momentum as the metal is subsequently encased in specialized layers of insulation. These coatings are engineered specifically to withstand intense thermal loads and resist the penetration of moisture. A deviation of only a few thousandths of an inch in the wire diameter or insulation thickness triggers immediate risks of overheating and short circuits. The manufacturing process transforms a slender strand of metal that at first glance appears fragile into a robust industrial component. 0.08 of an inch is the approximate diameter of a single copper wire capable of carrying enough current to power an entire residential home. Inside the thin insulating jacket, a steady stream of energy flows without interruption. It is visible how the equipment converts invisible atomic motion into the functional light and heat that fuels the continuous operation of the global infrastructure. This small component serves as a silent foundation for all electronic systems. Everything only gets more complicated when the initial mission of the wire is complete, yet the material does not reach a true end of its life. Copper possesses the physical property of being reborn almost endlessly through thermal processing. The plastic insulation is mechanically stripped away from the core. The remaining metal undergoes a cleaning process before being melted down in high-temperature furnaces and drawn once again into new wire. Each of these recycling cycles consumes significantly less energy than the initial mining and refining of raw ore. This reduction in energy requirements actively prevents the accumulation of waste and preserves finite natural resources. It is a closed loop where industrial technology and environmental sustainability coexist within the dimensions of a single unassuming wire. The molten copper eventually cools and solidifies, ready to begin the cycle of conduction once more. 200 to 300,000 pounds of raw ore are processed to produce just a single refined pound of copper. This extreme ratio defines the entire industrial sequence, proving that the value of the red metal stems not from its abundance, but from the staggering effort required to isolate it from the crust of the earth. Why must such a colossal volume of geology be disturbed for such a small yield? The answer lies in the chemical bonding of the planet. Copper does not exist in a pure native state, but remains tightly locked within ancient layers of stone, soil, and complex mineral compounds. At first glance, the extraction seems like a simple matter of digging, but in reality, it requires a synchronized cycle of drilling and blasting to strip away layer after layer of the Earth's surface. One can notice how the equipment gradually removes thousands of tons of rock every single day to reach the copper-bearing veins. But this is just the beginning. Modern copper mines operate as gigantic open-pit funnels that reach depths of hundreds of feet and span several miles in width. From a high vantage point, the camera glides along the tiered walls of these massive excavations that resemble man-made canyons. Hundreds of ultra-heavy haul trucks, each capable of transporting more than 300 short tons of rock, move in a continuous loop between the pit floor and the processing facilities. The sheer scale is difficult to comprehend, as the volume of material moved in just a few days would be sufficient to construct an entire city from the discarded rock. Everything only gets more complicated as the material leaves the pit. Primary crushing serves as the first essential step in breaking the structural integrity of the solid stone to free the trapped mineral particles. Inside the crushing plant, the ore undergoes multiple stages of reduction, transforming from massive boulders into gravel and eventually into a fine, consistent powder. It is visible how giant mechanical components exert immense pressure to shatter the rock. The process is only gaining momentum. The finer the powder becomes, the more effectively the copper-bearing minerals can be separated from the surrounding waste. Because without this level of precision in the grinding stage, the subsequent chemical separation would be impossible. Therefore, the powdered ore is funneled into the flotation process to begin its true transformation. Water, air, and precise amounts of chemical reagents are combined in large tanks to generate countless microscopic bubbles. One can notice how the copper-bearing mineral particles attach themselves to these rising bubbles, floating to the surface like a dark foam. Simultaneously, the heavier, worthless rock fragments sink to the bottom of the tanks. This represents the first true moment of isolation distillation, where the metal is finally recognized and separated from the rest of nature. The resulting copper concentrate now contains between 25 and 35% copper. This is a dramatic increase from the original concentration of 0.51% found in the raw ore. At first glance, the material is still not pure, but this concentration stage is decisive for the entire production chain. It effectively transforms mountains of seemingly useless rock into a concentrated metal resource with immense industrial value. The process is now ready to move toward the high-temperature metallurgical stages that follow. The copper concentrate sits in thick layers, prepared for the heat of the smelter. This concludes the initial phase of extraction and preparation, opening the road to the final refinement of the metal. 2,300 degrees Fahrenheit. This is the threshold where solid concentrate begins its final transition into liquid metal. Why is smelting considered the most decisive step in the entire metallurgical chain? It would seem that the previous crushing and flotation stages have already separated the valuable material from the waste rock. But in reality, the copper is still chemically locked within complex mineral compounds that only extreme thermal energy can break apart. The process is only gaining momentum. Furnaces receive the fine concentrate and subject it to a constant intense heat that forces sulfur compounds and various impurities to disintegrate. One can notice how these unwanted elements are either vaporized into the atmosphere or separated into a distinct layer of slag that floats on the surface. The heavier molten metal settles at the bottom of the vessel, marking the exact moment when the mineral ore truly transforms into a metallic substance for the first time. This results in the production of blister copper. At this stage, the material reaches a purity level of approximately 98 to 99%. It is visible how the metal exhibits a characteristic dark red color, appearing dense and exceptionally heavy. This substance already conducts electricity with far greater efficiency than any mineral form encountered previously in the process. From what was once raw rock and powdered ore, copper emerges as a functional industrial metal. But this is just the beginning. Once the copper has reached its molten state, it must be forced into a manageable shape for logistics and further refinement. The casting stage begins as the stream of liquid metal, glowing with a deep red intensity, is guided out of the furnace with calculated precision. It flows into heat-resistant steel molds, where the dimensions of the metal are controlled for the very first time. The equipment gradually manages the cooling phase. Within a matter of minutes, the internal temperature drops and the liquid copper solidifies into dense, rectangular blocks known as billets or ingots. These slabs serve as the universal standard for the metallurgical industry because they are easy to stack, store, and transport to distant facilities. It seems like a simple process of creating blocks, but in reality, this geometry is essential for the heavy machinery used in the next stages of processing. Everything only gets more complicated further on. Even after being cast into these crude plates, the metal remains insufficiently pure for high-end electrical applications. Tiny impurities are still trapped inside the structure, and while they are often too small for the human eye to detect, they are significant enough to reduce the efficiency of power transmission. To meet the rigorous standards of the modern electronics industry, the metal must undergo a nearly absolute purification step known as electrolytic refining. The crude copper plates are suspended in large tanks filled with a specialized electrolytic solution. When a steady electric current flows through the system, the surface of the metal slowly dissolves into the liquid. Each individual copper atom separates from the crude plate and migrates through the chemical solution toward the opposite side. One can notice how these atoms settle onto the cathode plates, forming a new layer of metal that is visibly brighter, purer, and more uniform in its crystalline structure. This reorganization happens gradually and without interruption. Each copper atom is essentially moved into a more perfect order to eliminate any remaining traces of contamination. The result of this slow migration is the production of copper sheets with a purity level of 99.9%. This is the specific chemical threshold required for the manufacturing of electrical power systems, delicate electronics, and high-voltage energy transmission lines. Transition to the next level of formation. After reaching this maximum purity, the copper is melted once again to be cast into long billets with a circular cross-section. This specific shape is ideal for entering the specialized machinery used in the wire forming process. From this point forward, the copper is no longer a heavy, immobile block of metal, but begins its physical transformation into a slender and flexible conductor. The molten stream goes further along the production chain. 100% of the heavy metal block begins its transformation into a slender conductor. The copper billets are fed through a rolling system consisting of multiple pairs of continuously rotating rollers. Why must the billet pass through such a complex series of mechanical presses? The initial metal block is far too thick for any practical electrical application. Each successive pair of rollers presses the metal closer together, reducing the diameter of the copper while significantly increasing its total length. One can notice how the billet changes from a thick industrial rod into a thinner and more perfectly round copper bar. This mechanical pressure does not only reshape the external form of the metal, it simultaneously compacts and aligns the internal grain structure, which ensures the future wire remains both ductile and strong. The process is only gaining momentum. When the copper finally leaves the rolling system, it has already taken the form of a rough wire. However, the diameter at this stage is still far too large for standard electrical use. It seems simple to achieve the final shape, but in reality, the metal must now enter the wire drawing stage, where size reduction occurs with nearly absolute precision. The copper rod is pulled with constant force through drawing dies manufactured from ultra-hard steel or industrial diamonds. Each die is specifically designed to be only slightly smaller than the one preceding it, often by a margin of just a few thousandths of an inch. With every individual pass, the cross-section of the metal becomes smaller while the length increases in exact proportion. Transition to the next level. From an original rod measuring only a few feet long, the wire can be drawn into a continuous conductor spanning thousands of feet. Throughout this entire mechanical progression, the wire is coated with a special lubricating solution. This liquid serves to reduce friction, limit the buildup of thermal energy, and protect the surface of the metal from abrasions. Without this lubrication, the friction would become intense enough to cause rapid overheating. Such heat would make the wire prone to cracking or sudden breaking under tension. Wire drawing does not happen in a single step. It consists of a sequence of gradual reductions where each adjustment is extremely small. It is visible how the metal gradually thins as a single wire typically passes through 10 to 30 different dies before reaching its final specified size. For example, from an initial diameter of approximately 0.5 inches, the wire can be drawn down to roughly 0.08 inches. It gets more complex further on. For electronic or signal wires, the diameter is reduced to even smaller dimensions. As the copper is continuously stretched, its internal crystal structure becomes harder and loses its natural ductility. For that reason, after a specific number of drawing passes, the wire must be lightly annealed. The metal is heated to temperatures between 600 and 800 degrees Fahrenheit to soften the structure again. This thermal treatment allows for further drawing without making the wire brittle or causing the strand to snap. Everything only gets more complicated as the final tolerances are met. More importantly, wire drawing does not only control the physical size, it defines the final surface quality. The more drawing stages the wire passes through, the more perfectly round the profile becomes. The surface gets smoother, which ensures the electrical contact properties remain stable over time. This technical precision creates the foundation that allows copper to function as an efficient and durable conductor throughout its entire service life. The material is ready to move to the next processing phase without haste. 71, 193, or even several hundred individual copper strands are required to form a single functional conductor during its entire operational service life. Why are these specific quantities of wires utilized instead of a solid core? After the drawing process reaches the target dimensions, these independent copper filaments remain excessively thin and possess a rigidity that makes them impractical for individual use. Only through the stranding process do they acquire the necessary durability and flexibility for real-world electrical applications. The copper strands are fed into a heavy stranding machine where dozens of rotating spools operate in perfect synchronicity. One can notice how the equipment twists each individual filament around a central axis at a precisely calculated geometric angle. This specific angle of rotation directly dictates both the bending strength and the final flexibility of the metallic core. A tighter twist orientation results in a more compact and physically robust center, while a looser configuration increases the overall pliability of the finished wire. But this is just the beginning. Every category of electrical conductor, ranging from thin household wiring to massive industrial power lines, relies on a unique and specific stranding architecture. These numerical configurations are never selected at random, as they must follow rigid geometric patterns that ensure the small wires fit together with absolute tightness. This creates a uniform round core with minimal internal voids, allowing for an even distribution of the electrical current across the entire cross-section of the metal. It seems simple, but in reality, this layout is what prevents the cable from failing under pressure. Mechanical stress is distributed across many small wires simultaneously when the cable undergoes bending, which significantly lowers the probability of metal fatigue or structural cracking. It is visible how the microscopic gaps between the individual strands serve a secondary purpose by helping to dissipate thermal energy more efficiently as the current flows. The process is only gaining momentum. Stranding successfully transforms disconnected copper wires into a unified conductive core that remains stable and ready for the application of insulation. 100% of the copper core must be protected before it can be safely integrated into an electrical grid. Bare metal at this stage conducts electricity with such intensity that even a fractional contact point would trigger a short circuit or create a lethal hazard for personnel. Therefore, the conductor must transition immediately into the insulation stage to become a complete cable. The stranded core moves continuously through a high-pressure extrusion system where materials like polyvinyl chloride, polyethylene, or cross-linked polyethylene are heated until molten. The molten plastic flows in a consistent tubular form, pressing tightly against the entire surface area of the metal to create a hermetically sealed layer. This material becomes a protective jacket that prevents the escape of electricity and isolates the internal conductor from the external environment. At first glance, the coating process looks automated and easy, but the thickness of this insulating barrier is monitored with extreme precision. If the layer is too thin, the safety of the component is compromised. Yet an overly thick layer makes the cable too rigid for installation and wastes raw materials. Diameter sensors operate ceaselessly during the extrusion phase to ensure the plastic coating stays perfectly uniform along every meter of the wire. It is visible how the cable passes through a specialized cooling system using either water or air immediately after leaving the extrusion head. This rapid thermal reduction allows the plastic to solidify quickly and maintain its exact cylindrical shape. The surface of the jacket becomes smooth and seamless, bonding firmly to the copper core held within. The material is ready to move to the next processing phase without haste. 100% of the insulation layer must reach a fully stabilized thermal state before the next phase begins. Why is the cooling process monitored with such technical rigor? It only looks obvious to move the wire immediately, but in reality, residual heat would allow the protective casing to deform under the pressure of the winding mechanism. Once the plastic is set and bonded firmly to the copper core, the cable enters the winding machine at a constant velocity. The wire passes through a tension control system that maintains a perfectly balanced state before reaching the rotating spool. It is visible how the tensioning rollers fluctuate to prevent the cable from becoming too loose, which would result in catastrophic tangling. It gets more complex further on. If the tension exceeds the set parameters, the copper core could stretch or the insulation could suffer permanent deformation. The spool rotates smoothly while a mechanical lateral guide moves back and forth with rhythmic precision. One can notice how the guiding arm lays the wire into parallel, tightly aligned loops without a single gap. Each turn is placed neatly beside the previous one to build layer upon layer of a uniform, perfectly shaped coil. The process is only gaining momentum as sensors continuously measure the total length of the wire. If the winding becomes uneven, the entire coil becomes distorted and difficult to stack for transport. Transition to the next level. When the preset number of feet is reached, the automated system stops the rotation, cuts the material, and secures the trailing end. Large coils require additional reinforcement in the form of plastic straps or steel bands to maintain their structural integrity. After the winding is complete, the wire is transferred to the packaging area to prevent contamination from dust and moisture. Each unit is wrapped in plastic film or heat-shrunk layers to protect the exterior from physical impact. The equipment gradually applies technical labels detailing the wire type, cross-section, length, and rated voltage. This stage ensures that the production date and specifications remain clearly visible for the end user. At first glance, this is a logistical step, but in reality, it prevents errors during large-scale distribution. Every batch undergoes a random inspection for appearance and packaging integrity before leaving the facility. The coils are placed on pallets or packed into standardized boxes according to industrial specifications. This final check ensures the material remains in its original quality during storage. Refining, forming, drawing, stranding, and insulation represent a long journey of technical precision. From deep copper mines beneath the earth to the final winding, the red metal undergoes a massive industrial transformation. What appears to be a simple product is the result of ancient geology and modern engineering operating without pause. Thus, the transformation of raw resources into the foundations of modern civilization reaches its completion.